In this video, I'm going to be discussing gauge selection and how to choose between all these different gauges in the different situations that we come across as inspectors and machinists. So by now, hopefully you've watched some or all the other videos where I talk about the different micrometers and calipers and hole inspection and surface plate tools, angle tools, everything that you have at your disposal. And now we're just going to answer the question of when you actually get to measure a part, how do you decide which gauge you're going to use? You have multiple options for all these features. Which one's best is subjective. So I'm going to give you somewhat of a systematic approach that I use. A lot of inspectors will develop their own approach, but I'm going to give you one that you can use until you develop one of your own. Oops. So, now that we've covered all these tools, how do you decide which one to use? Multiple tools can be used. So, for holes, right, we had a whole subject just on hole inspection where I gave you like 6 or 8 different tools you can use to inspect a hole. Here calipers, pin gauges, bore mics, telescope gauges, dial bore gauges. For outside lengths, across a feature, you can use calipers, micrometers, steel rule, height gauges, CMM. I have some of these here. And then inside distances, again, we have calipers, Joe blocks, pins, height gauge, CMM. Not to mention angles, threads, and profiles. So if you haven't watched those other videos yet, I generally recommend you watch the tool videos before you watch how to choose between them, because it takes a little bit of knowledge about how the tools work in order to make that decision. So it's more than just, is it physically capable? It comes down to print tolerance, gauge accuracy, and is the gauge physically capable? Oops, keep using it. Okay, so I look at some steps to decide, and then number one, first thing, and the reason it's first, most important, look at your print requirements. I always say, grab the print, take a look at your tolerance zone, take a look at the whole part itself, the way the datums are laid out, the way the implied datums are, tolerances, and come up with a game plan for how you're going to do each feature, how you're going to do the part as a whole. Number two, when you look at your part, looking at it in print is one thing. Looking at the physical part can change your mind. So when it's just in 2D, you may come up with some ideas, but when you actually pick up the part, look at it, maybe it's still in process, and it being in process, not finished, may change how you have to make your approach. But my second step, look at your part, consider how you might fixture it, consider any reference surfaces you might need. Reference surfaces could mean a granite surface, a 1, 2, 3 block, an angle block. It could also mean you need to use a reference surface from the part to get from one feature to the next. So you want to look at those, see if they're in good condition on the part, to see if they're good enough to use as references, or maybe they're still rough and unfinished, and it may not be possible. Number three, consider all your available tools. So I gave you that list on the previous slide, and there's more, certainly more tools that we've covered in this video series, and many that I haven't covered. But consider what you have. You can't, you're going to have to use what you have. And if you get to a situation where you need something you don't have, then you're going to have to order it. Hopefully you've figured that out before the part's ready for inspection, but occasionally you run into those situations where you realize you need something better than what you have. And then number four, I've come up with 8 questions that I ask myself when I'm starting out something new, and kind of a systematic approach to working through an inspection with a new part, new features, new tolerances, and how do I decide which tools. So we're going to run through those. Number one goes back to that previous slide. What is my tolerance zone size? So take a look at your print, figure out what your tolerance zone is. Use the tolerance zone to compare to the gauge accuracy that we've talked about for each gauge. We've talked about how accurate they are. And I have a video where I talk about accuracy, precision, uncertainty ratio, gauge R&R. Really goes into the details of when you can use these tools and when you can't. So with that knowledge, It helps you filter out, oh yeah, I've got a tight tolerance zone, can't use calipers. I've got a tight tolerance zone, that's internal features. Maybe I want to use pin gauges. Maybe I want to use a 3-point hole mic. So it can help you narrow down your list. Number two, what tools do I have available that are accurate enough for the tolerance zone? I just sort of started that discussion. So consider the uncertainty ratio, the 10-to-1 rule of thumb. Both of those will help you guide your decision, which basically says you need a gauge accurate enough for the tolerance zone. And what is accurate enough? Well, that generally speaking, a 10-to-1 ratio of your accuracy is, if your accuracy is small and you just needs to be smaller than your tolerance zone, should be a 10-to-1 ratio ideally. And in many cases, we settle for 4-to-1 or 3-to-1 because of manufacturing purposes. But if you have something like a caliper that has kind of a big accuracy issue compared to many of the other gauges I've talked about, sometimes a caliper is not accurate enough where the accuracy of that caliper and the tolerance zone are just too close to each other. You don't want to use it. So you're considering that. Once you have considered the tolerance zone and the gauges you had, you make a selection. Could be a micrometer. You ask yourself, do I need to fixture the part to use this tool? Do you need to set up on a rock? Do you need clamps? Do you need to hold it a certain way? If you are going to need to do that, maybe because you're using a height gauge, you have to do this stably and repeatably. So if your fixture is not stable or repeatable, you're not going to get the same measurement again. And if you can't do it again, you can't really trust any of your measurements, can't verify it. So make sure you're picking something that's not too complicated, that has some stability and rigidity to it. I've seen a number of people over the years set something up that's very complicated, and I say to them, all right, do it again. and they can't. They make that decision off of their first measurement, and they can't repeat it the next time it comes around because it was so tricky. You can't trust it that way. Question 4, briefly went over this already. Are any part references surfaces necessarily in good condition for the measurement? Will the error of the reference surface greatly affect the measurement? So, oftentimes it's not uncommon. Prints will, reference from one feature to another, and you'll be using that in the example of holes here, the location of these holes. Well, if you look at the print, they're called off the bottom surfaces and the side surface. And you'll oftentimes use a caliper, grab grab the bottom and grab the hole edge and use the distance from the edge to from the surface to the edge, and then use the radius and get the hole center. And sometimes this surface you're grabbing onto is in bad condition. It could be very bowed due to the manufacturing process. It could be unfinished. It could be chatter because of rough. It could be rough because of chatter. So sometimes, if I did all 3 of these holes, they're all different sizes, so I'm going to get different numbers with my caliper. That's not surprising. But when you do the math to find the center point, you might find that, there's a bow one way or the other. I might see that the chatter is really affecting each time I measure it. So some holes are in and some holes are out, and it's hard to repeat. So sometimes, even if the print, calls for, a certain reference surface off of the bottom, that it may not be usable. And so the part, the holes might be in the right place, in the right location relative to each other. And they might be in the right location relative to everything else, because CNC, if this was made on a CNC or even a manual, generally speaking, you're going to get everything relative to each other. But oftentimes it's the reference surfaces, the outsides and intermediate surfaces that, because of tolerance stack up or because of imperfections, will throw off your measurements. So it's something to be considerate of, something to be aware of. You can't necessarily control it as a inspecting it, but uh, you don't want to blindly trust. You want to take a quick verification. Some verifications you can do is maybe run an indicator and see if there's any issues. Feel it with your fingers. How smooth is it? Do you feel chatter? Um, run indicators up and down and parallel. These are just quick checks. There's nothing on the print that that you're verifying. You're just trying to see if things are flat, parallel, square, and good condition. So, question 5: Are there any obstacles or pitfalls that I need to avoid? That could be the part GDT errors, which is something I've sort of termed roundness, flatness, straightness, cylindricity, whatever. Just means all these features have some manufacturing error, and as you're measuring them, are you picking that up without realizing it? Is this hole out of round causing you to think the location's bad? Is the surface is the surface from the top edge to the bottom large because there's a taper, and the point where you measured it was large, and other points it's in. So imperfections in the part itself can lead you to make, certainly something's wrong, but you may not find it. And other times you may find it's in, that tapered surface I just used. You might find that it's in because where you measured it, it was in, but other places it's not, because you didn't measure every single point. So consider those. Other obstacles: radius and corner interference. So if you've watched some hole inspection videos or even micrometer videos, I've talked about how you have to avoid a radius and chamfers. So we will I'll do that one more time on the whiteboard here. So if you're inspecting a hole, for example, draw a hole, the bottoms of holes are going to have kind of a radius related to the manufacturing method. Even if it's 3D printed, there could still be something, any manufacturing method where that bottom of the hole is, there usually will be something. And if your anvil, say it's a 3-point hole mic, is grabbing onto the radius and not the sidewall, you're going to get a different diameter. You could do that with a caliper, even a pin. You could drop a pin down and say, oh, it stopped. I think the hole's small. No, it's just hitting the corner, radius here. So you want to avoid that sort of thing, because typically designs should have accounted for this radius, either controlled it with a call out for maximum size, or just made the hole deep enough to where whatever goes in the hole isn't going to be touching the radius. Either way, as an inspector, you want to avoid those. If you need to verify how big it is, then that's what you need to do because the print requires it. But otherwise, you're okay. For an external feature like our step shaft drawing, right here at this corner, I drew pretty sharp, but odds are there will be either some sort of straight or radius to it. And when you're grabbing on with a micrometer from the outside, you do not want to grab onto that radius either. You want to grab away from it so that you're getting a good measurement. So you have to think about that. Sometimes that gets overlooked because people are so focused on designing the part and maybe even making the part. They overlook how do you inspect it. And sometimes due to the size of gauges, you run out of real estate to grab onto without hitting something. So, just keep an eye out for it. Be aware of it because it may affect your measurements. Other things like burrs, sometimes there'll be sharp edges left over and your gauges will grab onto those that are, protruding and messing up your measurement, and they should be removed. Once they're removed, everything's okay sometimes. If you watch the hole inspection video, I even found a burr inside. Can't remember which hole it was now. I think it might have been this hole. a burr that stopped the pin gauge from going through. But otherwise, once that burr is removed, I've got tons of clearance, but the go side wouldn't go. It was just right on the edge of this tolerance zone because of the burr. When the burr is removed, I'm gonna be back in the middle of tolerance, and everything will be great. And then that gauge handling. So, do you have good technique when you're using your gauge? Sometimes you might be working with a tricky part, and yeah, your gauge is capable, but the way you have to hold it can be awkward and not give you good registration. And this is usually a problem with bigger parts or parts inside a machine, and you've got other things to navigate around to get your gauge on. But with like large mics, for example, I don't have any large mics here, but if you had a 20-inch or 15-inch micrometer, well, handling that with two hands is a lot different than handling a 0 to 1 mic with one hand or two. But you have to change your technique when you're using this inside micrometer at 4 inches or 3 inches versus 28 inches or 30 inches makes a difference as well. So parallax error, sometimes when you're using an indicator, you may not be standing in a position to get a good angle of sight, and that may lead to some parallax error. So just remember to keep your eyeball straight on. I talk about that in the surface plate videos, so be aware of those. Now, after these 5 questions, you can actually measure the feature. You've thought about the gauge you're going to use, the accuracy, the tolerance zone. You've inspected the surfaces you're going to use and say they're good, or maybe they're not, but you have to try. So now, number 6, was the measurement a good one? Do you feel confident in it? Do the anvils get good registration, solid, repeatable, or were they rocking? Were you twisting and could get any number that you wanted because maybe there's some taper, some form error? Did you get good pressure? Is it repeatable? Were there any obstacles or pitfalls that you didn't avoid that affected your result? You'd look at it, you're like, oh, this doesn't make sense. I must have missed something. Oh yeah, there's like a chip inside or some extra material that just you didn't notice when you were looking at it, but still in there. I can't tell you the number of times I've measured a blind hole, and my micrometer or my pin stops. I'm like, why is it stopping? And then I look inside, and there's a giant chip ball in it, and it's only 1 out of the 10 holes that was drilled, but I just happened to pick that hole first and say, what's going on? Oh, there's a ball of chips in there. So stuff like that can always mess up your inspection. Then ask yourself, number 7, am I confident in the measurement? Think about, where did the measurement land in the tolerance zone? Were you close to the edge of the tolerance zone? Were you right in the middle? If you're close to the edge, do you need to check it again with something better? So again, I have a video where I go a little bit more detail about that, but we'll review quickly. If you've got a linear tolerance zone, all right, you have a minus side and you have a plus side and you have your nominal. And you ideally, as inspectors, machinists, it's great when your measurement lands close to the nominal all the time. Every once in a while, you might end up at one extreme or the other, and you've got to ask yourself, every gauge we use, right, no matter which gauge it is, it has a plus or minus accuracy. There's a few exceptions, but there's a plus or minus accuracy that might, in reality, that part might be out of the tolerance zone, but the gauge has a little sensitivity, or for lack, has a little accuracy, uncertainty that actually whatever you measured it could be in that range as well. So it might be out. So in situations where you end up, close to the edge, you may ask yourself, "Ooh, I'm close to the edge. Do I need to use something better so that when I, repeat that measurement and I get, right on the edge, but I use a more accurate gauge that has a much smaller accuracy, um, has a much better accuracy, smaller uncertainty zone, and you're within tolerance at all cases." So this might be going from a caliper to a micrometer. It could be going from a steel rule to a caliper. It could be going from a micrometer to a CMM. It could be going from many different steps in accuracy. So so sometimes it's true. You'll get on the edge of your tolerance zone. You just gotta ask yourself, well, okay, the gauge said I'm in tolerance, but is it still possible that the part is out of tolerance and my gauge isn't picking it up because I'm right on the edge? So number 8, once you've gone through everything, this is kind of an improvement, continuous improvement, sort of learning opportunity. Could I do this with a different tool that is faster and maintains confidence and accuracy? So sometimes you maybe picked a gauge like a micrometer that is very accurate but may be overkill. You thought, yeah, I got to use the micrometer. I want the accuracy. And then, it takes a little bit longer to use and read micrometers. Not a whole lot. I mean, it's debatable. I've had a number of people say to me, yeah, I'd rather use a micrometer than a caliper. And that's personal preference. I'm not going to argue with that. But generally speaking, calipers will be faster, easier, more variety of features it can do. So there might be situations where you could still maintain the accuracy that you need at a minimum. You're giving up a little bit of accuracy by changing, but you still get at a minimum what you need, and you can do it faster and still maintain the accuracy. So there's other situations too. Maybe you use the CMM and you thought, well, I need to use the CMM, and you're like, oh, well, now that I went through all this trouble, actually I could have just done this on hand tool or a surface plate and gotten the same confidence in my measurement. So with enough experience, when you have all these 8 questions that you're running through in your head, you're going to consider these naturally. This is kind of something that I do occasionally when I get something brand new that I need to inspect. But most of the time, when I'm just working with tools and parts that I'm familiar with, I'm going through it naturally very quickly, grabbing the gauge intuitively that I want to use based on looking at the part and glance, looking at the print. Obviously, still have to always look at the print. But I know some people, they're not really taking pride in their work, so they don't consider if what they're doing is good enough or accurate enough or it can be improved. Some people kind of just rely on what they know, what they've used, and not looking at the bigger picture for opportunities to improve, to get better with the tools, get more insight into the part by studying the print. So I recommend you definitely look for those opportunities to improve and base it around your tolerance zone and what gauges you're going to pick. But you'll learn new things. You'll learn that you could use other gauges and improve accuracy, improve speed, and that'll be beneficial for your careers. So going through those 8 questions, right, there's throughout those questions or whether you're using them or not, there's some major considerations that you have to consider when you're making a choice about what gauge you're going to use. And every choice may not be weighted the same. Some are minor, some are critical, and many are just average, have typical impact. So from a metrology standpoint, what you're considering: tolerance zone, the gauge accuracy, and the fixtures you're going to use. from an inspector standpoint, the human standpoint, you got to have experience with the tool. I could tell you, yeah, go use that dial bore gauge, right? It's going to be the gauge you should use in this situation. If you've never used a dial bore gauge, they're tricky for me, even though I have used them. So sometimes does it do you any good to use a gauge that you don't know how to use? Or do you use something you do know how to use that's a little less accurate but will get you a better result? Those are challenging questions. I've been in those situations, and so you make that decision. You set up the new gauge, learn how to use it. Takes longer. Definitely takes longer, but sometimes you need to. Sometimes it's worth it. Again, experience with the gauge, proper technique, and then sometimes experience with the part. You may be getting parts you're just not familiar with how the prints are laid out. Every time I look at a new print style, it takes me a while to get used to it, to find where the datums are, to recognize them, the notes, how it's applied. Every print is going to be a little different in style, depending on the person that made it or the company standards for making prints. So that can be challenging. And you might be getting a part, wow, it's like you might have been someone who's been inspecting lathe parts, or and then all of a sudden you start inspecting mill parts, and it's just a whole nother ball game. There's something to learn. So changing manufacturing processes, getting new parts, need some experience. And then business wise, you're always considering time and money. Quality control is kind of the art of minimizing costs while maximizing quality, and there's always a balance, because you could guarantee 100% quality on every single part, inspect 100%, maybe even multiple times if you needed to, but that can be costly. So choosing the right gauge is a way of minimizing cost and maximizing quality, and training yourself to do that quickly and repeatably is a great way to save some money, still guarantee quality. I've got some other topics, sampling, and where we talk about maximizing value of inspection while minimizing cost. So first of all, I've said it many times, and I want to hammer this home: always compare the tolerance zone to the gauge accuracy. So know what your gauge accuracy is, know what your tolerance zone is. Do that uncertainty ratio, 10-to-1 rule of thumb. Do that, figure that out. You use the gauges enough, you'll know right away. And then you just check with the print. Consider if fixtures will help or hurt. Sometimes setting up complicated fixtures you think will help you, and by the time you do it, you're like, this isn't helping. Maybe this is introducing a new error. I've seen a number of people tell me, oh yeah, I'm looking at the part. We're both looking at the part. He's like, oh yeah, I'm going to set it up and hold it and twist it. And then I'm going to drop a caliper down this direction. And by the time he's done, it's so complicated, it's not repeatable. So it happens. I could see that, sometimes I can see that right away. The other person doesn't. Other times I don't see it and they do. And sometimes they're right. You got to try sometimes. So last one, consider your experience with both the part and the tools, and what tool combination optimizes your inspection. That's taking everything into account. That's factoring in your own experience. Like I said, sometimes I've been in situations where I should have used a more accurate gauge, but I didn't know how to use it. So I made a substitution, sometimes with something, the dial bore gauge is an example where, when I wasn't so familiar with them, I might have used a whole mic, still pretty good accuracy, but doesn't reach the depth that the dial bore gauge is. Or I might have taken it to a CMM because it's easier to use a CMM than the dial bore gauge, and you still get that same accuracy. I've relied on the CMM many times for cases where, I could have used a hand tool or a surface plate tool, but it's easier with a CMM, and I still get that accuracy, and that's okay. And then as I got better with all the tools, I started to use the surface plate tools more and more, and the hand tools more and more, until I got to a point where I was comfortable with all of them. But it takes a while to develop that. With the wide variety of tools in the industry, it can take time. So here's an example. Okay, large open tolerance outside diameter, and you have no large calipers, right? I mentioned it's large and it's open tolerance. So a caliper would be a great thing for an outside diameter if you have one, but there's none available. So do you want to use a large OD mic? Certainly possible. It's open tolerance, so you don't need to worry about too much about making a mistake. As long as you have kind of good technique and follow the right steps for aligning the anvils, you'll, even if you are not great with it, you might be off a thousandth. But with an open tolerance, that may not matter. But even then, in that situation, if I can get it on a CMM, it's going to be very easy on a CMM because I don't have to worry about handling big tools or handling big parts. And then, there's always the business aspect, as I said, time and money. And so the most accurate gauges are not always the best choice if they take excessive time or cost the company money that could be spent elsewhere. So this is kind of just a comment about the industry. Feel free to rely on your print, your gauge accuracy to be your justification, right? If somebody says, well, that's going to be too expensive, it's going to take too long, this is the ultimate authority, the accuracy and the gauge print. You can rely on those. Now, sometimes those conversations can lead to a compromise that still satisfies accuracy and print. So it's good to have those conversations, but sometimes you may need to rely on the more expensive, more time-consuming method, and then maybe other cheaper, faster methods that still satisfy what needs to be done. Because it can be tempting. I'm not criticizing anybody that wants to use the CMM for everything. That's that comes down to comfort, that comes down to experience, but there are other ways to do parts, and so just because the CMM is most accurate doesn't mean you always need to use it. And there may be situations where it may take a long time to unload the part, interrupt the CMM programs that are already running and put your part up and do it, write a program and measure it. You can do it right there on the machine sometimes with a hand tool, or take it to a surface plate, do it right there. So that's kind of an aside, but it leads us to our conversation. Well, there is a business aspect to everything we're doing. We're trying to maximize value, as I said. So most quality control out of the least dollars. And if you look at what the business aspect is considering, they're considering the same things. So it may not be the accountants and the engineers and the salespeople. That's not what I'm talking about. But the people in charge of production, the quality managers, the production leaders, the experienced inspectors, all of these have a dollar amount associated with them as well. So tolerance zone, gauge accuracy. If the tolerance zone is open, it generally leads to less expensive manufacturing, which leads to less expensive inspection. And when it's tight, the smaller the tolerance zone, the more expensive the feature, more expensive manufacturing methods, the more expensive inspections. Same thing with gauge accuracies. When you need to use more accurate gauges, that means you're, generally speaking, spending more money on that inspection. Not necessarily buying. You may already have the equipment. You may say, well, it's not costing me anything to use it. But in time-wise, using these more accurate gauges sometimes means more time. It can be more wear and tear and more calibrations, more repairs as well. So, the business aspect is considering all of this, and there's a dollar figure, that nebulous dollar figure that could be associated with this. And the business aspect is why inspection is needed, and why I'm kind of making this course, the Pragmatic Metrology video series, to try and train people to do these inspections, use this equipment with the least amount of expense involved, right? You want to get people trained, you want to get people confident, and you want to, obviously you want to minimize how much money that takes, whether people come out of a that people are hired on and they get trained, whether that training lasted a year and it took $100,000, which is some estimates I've heard that it takes $100,000 of time and money to train a person in a new job, or maybe you can find a cheaper way to do that faster and still get the same result. So this video series is kind of meant as a way to fill some of that need. In a perfect world for a company, it's possible to automate just about everything on a CMM or other robots, and then no experience is needed, besides programming the robots. But otherwise, in a perfect world, you don't need to use these hand tools. Everything's automated, everything's on a program, and so that minimizes costs in the long run. So, you may have investments in the robots and the programming, but overall, the trend is that would be more cost effective than using these hand tools. But the reality of manufacturing is you can't automate everything. Even CMMs cannot do some of these measurements that need to be done by hand tools or surface plate. So as much as businesses might want to move away from using these tools, they're always going to be around. They're going to be around for decades to come, until some revolutionary method comes about that's cost effective. But for now, it's good to learn how to use these gauges, because it's going to be more cost effective than automation in many cases. Not all, but I've worked at a company that if you're only making 10 parts and you have thousands and thousands of parts in that lot size, does it make sense to do automation on all of that? Maybe it doesn't. Now, if you're only making one part and you're making thousands and thousands of them, that's a situation where it does make sense. So every business is going to be different, but it's going to be important for you, as watching these videos, to learn how to choose between the gauges when the business decides that it's up to you to rely on your experience. And so that's hopefully all these tips will help you and kind of make the business aspect happy as well. So we'll kind of in the ideal, kind of the utopia of manufacturing, everything's easy, right? So I've talked about you have to make these decisions. Well, in the ideal world, the decisions are easy and obvious and straightforward and follow a clear line of reasoning. So designs revolve around production capabilities. First one, you're not asking the production of the part to be to go beyond its capabilities. Many designs actually do that because people designing simply are not familiar with production capabilities. And every part's different, so you may not realize going from one part to another in a design, one part was handled no problem. New features may be similar, but different tolerances, different feature shapes may be very difficult. And maybe the designers, they're designers, they're not necessarily supposed to know that. Hopefully, they should have some reasonable experience. And there's other people like manufacturing engineers and production leaders that can guide the design into an area that's satisfactory to production and functional design. But that's where hopefully you want to start, where the designs revolve around production capabilities. Production stays within inspection tolerances, and even production tolerances, if they have them, will be tighter than inspection tolerances. And parts are easily inspected on a pass-fail basis using the most optimum methods. So that's ideal. That makes choosing the gauge easy. That means applying the gauge and pass, reject easy. But that's not always true. And that's another reason why I would like to create this video series. Because management will say, what you want to do, this ideal world, it's taking too much time, it's taking too much money, it's taking too much resources. And we need to move forward with what we have or what we can do, and we'll have to make the decisions along the way. And then those decisions get a little harder, more nebulous, not cut and dry. And there's time involved in making decisions. I mean, there's discussions that happen, there's trial and error. I've mentioned, hey, you might have an idea to set something up, spend 20 minutes doing it, and it doesn't work. Trial and error. You move on to the next idea, plan B, plan C, plan D. I've been there. And oftentimes, that last bullet point, inspectors are challenged to just make it work. If inspection's not involved in the design process, production process, we can be overlooked in our capabilities. So they may give us a part that has challenging features that could have been easier to inspect with modifications to design or production. But because of the way it was designed, because of the way it was produced, it makes it challenging for inspection. And you just say, well, it's designed this way, it's made this way, you just got to inspect it the way it is. And so that comes down to gauge selection and fixture setup and all the questions I outlined before. So the cliche, the one I've heard for years, good, fast, cheap, pick two. You can't have all three. Some companies work towards it. Some companies get real close. Probably the companies that are performing the best in their industry, in their market, are probably close to getting all three. But because of competition, because of even employee turnover, things change and you're only going to get two. So I would say, right, as quality people, we want it good, and then fast or cheap is always the balance. Quick and expensive, fast or slow but cheaper, or however. So you're always playing that balancing game. So I've probably spent about a 10-minute detour on the business aspect of it. We're going to get back into the metrology inspector aspect of it. So we get back to basics. Most gauges will come with an accuracy stated by the manufacturer. It might be in the catalog, maybe in the paperwork that comes with the gauge. And they vary slightly by maker. So you compare a depth micrometer from 2 or 3 different manufacturers. They'll have different accuracies slightly. Generally speaking, they keep up with each other. Some cheaper ones will have bigger problems, and some cheaper ones that you may find on the internet, no-name brand or import brand, depending on what you're inspecting, you may want to stay away from those altogether because you don't know the accuracy. They may not state it. It may not be. You may not get the same accuracy that you get from a known name brand manufacturer. So keep that in mind. Lesser gauges, in this series, I don't cover a whole lot of steel rule or tape measure. We do a little bit of feeler, radius, angle gauges. A lot of these are reference only, and you just, you can certainly calibrate these. You can certainly make these a part of your inspection process, but in many applications, they're used as a reference to check that manufacturing is doing things correctly. And so you gotta be aware of that. Some of these reference gauges just aren't nearly as accurate as the calipers and the micrometers and all the other gauges I've covered. So it's not true of all of them. Certainly, like the radius and the angle gauges, actually made pretty well, but the application of them is sometimes for reference only. So I've got this chart. I've talked about accuracy. I've talked about the 10-to-1 ratio. And I'm going to have this chart on the website for you to download in a one-page format. But we're going to go over this reference guide for the different gauges when you're choosing between them. It helps to have a single source reference guide. And what we use for making our decisions are resolution and accuracy. Resolution feeds directly into the total uncertainty ratio on the right column there. So this resolution is directly proportional to the uncertainty ratio. So 3-to-1, 4-to-1, or 10-to-1. You essentially multiply, 3 times the resolution or 4 times resolution, or 10 times resolution. So I'm giving you a few of these. And this is going to be your minimum size tolerance zone. So when you're looking at a print, looking at print and you're looking at your tolerance zones, if you're going to use a caliper at a 3-to-1 ratio, you need at least 3 thousandths tolerance zone, hopefully bigger. And if you're going to do it at a 10-to-1 ratio, which is what we want, you're going to need at least 10 thousandths tolerance zone size, if not more. So, the accuracy itself is not playing into the uncertainty ratio, but the accuracy is that plus or minus spread that I talked about on this whiteboard earlier. It's that how much plus or minus accuracy you have every time you take a measurement. So those are both important, and I've given you a few, I've simplified it. You can certainly get very specific with your resolution and your accuracy down to the exact gauge you're purchasing. But these are some general industry trends I've seen comparing the manufacturers. And for years, I've had to purchase this equipment, and I've been checking out their resolutions and their accuracies to make the decisions that I need to inspect the parts that I have. And so, generally speaking, you have your calipers, your dial bore gauges, height gauges, indicators, drop, and test. They have variations in resolution, accuracy, and so that'll help you. You look at the uncertainty ratio and you look at what size tolerance zone you have. If your tolerance zone is bigger than the uncertainty ratio that you want, let's say you want a 10-to-1 ratio, this will tell you how big your tolerance zone needs to be at a minimum to use that specific gauge. So that can help you make a few decisions. I have a note on the bottom here. Height gauge and indicator accuracy is also length dependent, and the chart is not accounting for that. So CMMs, height gauges, anything that travels a large distance, there will be an accuracy if you move a couple of inches, and there will be a bigger accuracy error, a bigger error added if you go a large distance. So height gauges are one of those tools that travel a long distance. Indicators drop indicators can get 2-3 inches in stroke. But this is just displaying kind of the manufacturer minimum accuracy that they'll state, that they'll stand behind when a manufacturer says, this caliper is accurate within, let's say it's plus or minus 1,000th in the 0 to 6 range. They'll guarantee that, and when they go to measure something with it, they'll say, anytime we measure something that we know is 3 inches, like in the case of this Joe block, we'll be within 1,000th of that Joe block. So with this camera, I don't know if you can see on the front, but on the secondary camera, I was getting 3 inches, or 2.999 when I had a little bit bad angle, but that's what they're saying. So whether I use a caliper, whether I use a micrometer on a 1-inch block, it's going to be the same thing. They're going to say we're going to be within the accuracy that we state in our catalog. That's kind of our guarantee for how accurate, comparing to a known standard. So that's a few gauges. We will move on. I will show you just a few more. So I have all the micrometers on one slide here. The most common micrometers, I should say. So, bore micrometers, resolution is typically around 2 10,000ths or 2.5 10,000ths. Depth micrometers, resolution is actually only 1,000th in most cases. In most cases, these don't have that vernier scale accuracy on there to help you. So you're gonna have to kind of judge where that last digit lands, as I talked about in the video where I talked about vernier scale. ID micrometers, again, do not have resolution past 1,000th. And OD micrometers, the most accurate we've seen on the resolution anyway for micrometer, you get down to a 10,000th of an inch with the vernier scale here. And then you have all of the micrometers have sizes as well. So the size range, sizes can range for all of these tools, and the accuracy will change. You'll notice that the accuracy gets larger and larger and larger as the gauge gets larger, which makes sense. You have bigger pieces involved, more travel involved, more accuracy error. But the uncertainty ratio remains constant. No matter the size, it comes down to the resolution. So the uncertainty ratio is helping you choose the gauge. The accuracy is helping you determine if your part is going to be within tolerance based on the accuracy of the gauge. And we have one more. We'll talk about the solid gauges and the CMM. So solid gauges would be Joe blocks or pin gauges, gauge pins, and gauge blocks. And they don't really work the same way as the variable gauges. They are manufactured to a certain accuracy. So you see on the gauge blocks, class XX, class Z, ZZ, and they will tell you the maximum amount of error from the nominal. So when I have the 0.90 ZZ, the maximum amount of error that the manufacturer will guarantee is 2/10,000ths. Actually, this is a bad example. I was reading off of the I have a mistake on the slide here. Confused me. So forgive me. The gauge pins here should have been in this section, and the gauge blocks should have been here. So these are the accuracy numbers for gauge pins, and these are the accuracy numbers for Joe blocks. And I have the labels flipped here. So I realize that because 2/10,000ths error on a Joe block would be huge. If you look at the accuracy of the Joe block on the slide here, the even at the lowest level, the grade 3 maximum error is, I can't even read that number, it's like 4 millionths. So it's going to be manufactured to an extremely tight window, which means you can use it in many situations and use it as a reference, because it'll be manufactured to a much, much, much greater accuracy than your gauges operate in. So you can use it as a reference. The gauge pins, as I was trying to explain earlier, a class ZZ pin might have 2/10,000ths of an inch error, which is a little bit significant. For a gauge pin application, it's not that significant, but 2/10,000ths of an inch is something we're familiar with working, is a size of we're familiar working with. So there'll be a little bit more error in the gauge pins than in the Joe blocks. But again, these are maximum errors. These are not plus or minus. There's no plus or minus involved in that. Those are maximums. Maximum amount of error, either positive or negative, but not both. And in fact, when I talked about gauge pins in the whole inspection video, I talked about how gauge pins are sorted. So all the ones that are bigger than nominal are in a set called the plus set. All the ones that are smaller than nominal are in another set called a minus set. So if you haven't seen that video, check it out where you can learn more about the gauge pins. And I will fix this slide. CMM. So CMM, I have some typical numbers here in a chart for a 5 micron resolution CMM, maybe about 24 inches wide, maybe about 18 inches of stroke and 24 inches of depth. Kind of a medium-sized CMM, definitely not the smallest or the largest. And these accuracy numbers, they're highly dependent on length. So they're highly dependent on the hardware. So when you're buying a CMM, if you've never used a CMM or never researched how you purchase them, you buy the CMM, but you get to choose the head that's installed, which is the probe head. It rotates around. You get to choose the probe that goes on the head, which are interchangeable, have different sensing parameters and different applications, different capabilities. And then you get to choose the stylus, the actual point that makes contact with the parts. And you can choose the shape of the stylus based on your applications. It could be spheres, could be discs. You can have multiple tips so that you can use multiple tips, measure faster. So all of that plays into the accuracy. I've given you some typical numbers that you could use. And if you wanted to research whatever CMM you're using, you can do that, and it will change these numbers. There's a very sort of complicated formula that these numbers come out of. I don't feel like it's necessary to share the formula with you, but the Gage, the CMM manufacturer will tell you the formula so that you can calculate it yourself, but it is quite complicated. It takes temperature into effect, it takes all of your hardware into effect, and it takes the length of the measurement you're doing. As I mentioned, with a height gauge, you might be getting 12 inches or 18 inches of stroke, and with a CMM, you may be even getting larger than that, and it will take into effect how large you're measuring. So measuring something small on a CMM will give you a better accuracy number than measuring something large. And sometimes that difference can be a problem for your uncertainty ratios, or sorry, for your accuracies. Those accuracies might end up bigger than the tolerance zone or close to the tolerance zone. But you can still calculate an uncertainty ratio to help you, give you a ballpark for choosing if you're going to use a CMM or not. And you'll notice the windows are much, much tighter. For 10-to-1 ratio, 2/10,000ths with a 5 micron resolution machine, which is many tolerance zones are bigger than 2/10,000ths. Some are not. So you'll still need to decide if you can use a CMM. It's one of the more accurate gauges, and as you compare all these numbers, you'll see why. But just still, it's not universally applicable to all situations. And then let's do a quick review about the tolerance zones. I did sort of draw this on the whiteboard earlier, but if we looked at on the top side a caliper tolerance zone, kind of a big tolerance. Big tolerance zone, plus or minus 5/1000ths from the nominal. And you compare that, sorry, I'm talking about accuracies. And you compare that to the micrometer, if you put them on the same scale. This is kind of what I'm talking about when you compare a caliper's typical 10-to-1 ratio tolerance zone to a micrometer's. You get more accuracy out of that. So if your nominal measurement up here, if I drag this 4-section square over towards one of the edges, it might pop out, that plus or minus right and left, it could pop out of our tolerance. But if you use the micrometer and you kind of zoom in on your accuracy, you may still be in tolerance because our accuracy has changed from 2/1000ths to 2/10,000ths, our plus or minus window. So this is the plus or minus applied to each other at relatively the same scale. So I hope you can kind of see that, but you'll see this is why the micrometer is a much more accurate tool because of the 10-to-1 ratio that you can apply. So all requirements have a tolerance zone, right? We all have no matter what you're inspecting, machine parts, plastic, sheet metal, whatever, you have a tolerance zone. All gauges have an accuracy uncertainty, that plus or minus, that from a nominal. And you ask yourself, what if your measurement is close to the min or the max of your tolerance zone? You have to calculate the difference. If I'm at the extreme of my gauge, am I outside of the tolerance zone? Oftentimes I'll say repeat it, double check it. If you're right on the edge of tolerance, do it again, see if you made a mistake. One way or the other, you might get out of tolerance the second time you check it, or the third time. And then you might say, I'm still right on the edge of tolerance. I got to find something more accurate so that I can get more certain. And you still have to verify the situation. So we're going to walk through an example. Let's say we're inspecting a hole. Let's say it's an outside hole, and your print requirement or outside diameter, so not a hole. Outside diameter could be like our step shaft. Could be a diameter like on our step shaft. It's 4 inches plus or minus 15 thousandths. So you have a 30 thousandths tolerance zone, which makes your caliper acceptable. We talked about before, pretty much you need 10 thousandths at a minimum to use a caliper, and we've got 30. And we have our accuracy of plus or minus 2 thousandths. So again, plus or minus 2 compared to 30, as long as we're relatively near the middle, we've got no issues. So we do our caliper measurement, right? We grab our micrometer, or we grab our caliper, we measure across it, and we look at it. And this is not the same part as the example, but we look at it and it says it's 4.014. All right, we have plus or minus 15 from 4. So we're right on the edge of tolerance. And we know every caliper measurement we take is plus or minus 2 because of the accuracy of the caliper. So we could be out of tolerance by 1,000th, right? If you're at the extreme plus on your caliper, which could happen, calipers are not the most accurate gauge. So what do we do in this situation? We're going to re-verify with a micrometer. So I'll grab a 4-inch micrometer, something with a 4-inch, maybe a 4 to 5 micrometer, and we'll measure across our part, and we'll take a look at what we get with the micrometer. The micrometer said 4.014 6/10. Okay, so we added 6/10 compared to our caliper because our caliper doesn't have that resolution, or that accuracy either. So now we ask ourselves, is 4.0146 mean the part is within spec? And so with with the micrometer, our accuracy plus or minus is 2 10,000ths. So plus or minus 2 10,000ths from here will take us between 4.0144 and 4.0148. Either way, we're in spec. So we took a less accurate tool, we measured our part, and we said, oh, we're right on the edge of tolerance. We might be out of tolerance because of the accuracy. Let's grab a more accurate tool. So we grab our more accurate tool and we're like, oh, we're right on the edge of tolerance. But because of the gauge accuracy, we haven't gone out of tolerance. The part passes. So the less accurate tool couldn't verify it, the more accurate tool could. And this scenario I'm going through, in industry, sometimes it's going above and beyond what's required. Sometimes industry will say, look, you've used your caliper and you verified, oh, it's the caliper's less than the specification. Forget the plus or minus accuracy. But that's not what I want you to do. I want you guys to be thinking and considering your quality, your inspection, even machining, production. You want to be making good parts. So you want to, if you're on the edge, you want to verify that you haven't gone out, because it really doesn't matter if it passed your inspection with the gauge you used. You did everything right. You used a calibrated micrometer. You used it correctly. Because of the it's same as using a scale. Could you really tell that with a scale? It's no different just because it's a caliper. So going above and beyond to verify it is what good inspectors, good production people will do. Verify your measurement. Make sure that the part is going to work for its function and be within spec. But if, some places don't do that, some do. I always do, if I'm right on the edge of tolerance, try to verify with something more accurate. Oftentimes, there's not a whole lot of room for error in assembly. The way tolerances have shrunk over the years, more and more precision, more and more accuracy required, smaller tolerance windows, and manufacturing has increased. Accuracy's gotten better, inspection's gotten better, so everything's getting tighter. So there's not a lot of room for error. If you're out of spec, it may not work for you. So I want to thank you guys for watching this video. I hope you learned something about gauge selection and the steps that I go through. I know it's not cut and dry sometimes. Sometimes it is, but a lot of it is down to experience that you will gain over the years. Hopefully, I've given you a few things to think about to help you in those decisions while you're still while you're still early in your careers, or even if you're already well into your career watching this. Hopefully, you either appreciate the steps I'm going through, or you've learned something about how inspectors choose their tools. So I'd like you to check out my website, pragmaticmetrology.com, where I have more of these videos, more resources for you to download and use in your careers. And I need to thank the Laney